welcome to RF transceiver design course, and we are discussing about the power amplifier design. We have defined a different class A, B, C, D, E, F in the last lecture. Now we will see that how we will see in this class about the linearity and how we can do the impedance matching, and one widely used topology which is a cascode output stages. So, cascode is also used in the output stage, and what are the advantages and disadvantages using the cascode stages. So, here when we use the cascode stage, one can choose the VDD, where VDD which is equal to the half of the maximum tolerable voltage of the transistor, means which is a half voltage, and uh, what will happen that but there is a two penalties. The lower headroom limits the linear voltage range of the circuit, and the proportionally higher output current for a given output power leads to greater loss in the output matching network, reducing the efficiency. So, we need to have a two penalty that we need to give. It will reduce the efficiency, and it will have a lower voltage headroom, limits the linear voltage range of the circuits. So, if we see the Vx which is full swing, and Vy which is a Vb minus V threshold. So, the cascode device shields the input transistor as Vx rises, and keeping the drain source voltage of M1 less than a Vb minus Vth2, that is a V threshold 2. Now, if we try to see the linearity consideration for this, the for circuit A, we can get the swing which is VDD minus V of the cascade minus VDS2, that is a drain to source voltage of 2, plus Vth equal to Vo plus Vm. And for circuit B, it is a VDD minus, so for circuit A it is VDD minus Vp, that is VDD minus Vp of this cascade stage minus VDS2 plus Vth equal to Vo plus Vm. And for circuit B, which is this, Vo is a input voltage swing, and Vm is a mid voltage at the input. For circuit B, VDD minus Vp cascade plus Vth1 equal to Vo plus Vm. So, what it follows that Vp common source amplifier equal to Vp of cascade plus VDS2. So, this VDS2 is added, and this is a V cross. So, for circuit A we can write it down VDD minus Vp cascade minus VDS2 plus Vth equal to, this is for this circuit, and for this we can write it down VDD minus Vp common source plus Vth1 equal to, so if V threshold 1 and this is same, we can get a Vp common source which is equal to Vp cascade plus VDS2. So, the common source stage remain linear across the wider output voltage range than the cascode circuit does, and at low supply voltage cascode output stages offer only a slight voltage swing advantage over their common source counterpart, but at the cost of efficiency and linearity. So, linearity degradation is happening because of the stack transistor, and that will affect the linearity as well as efficiency. Only advantage of this circuit is stability. So, the stability of this circuit is better compared to the what we have seen a simple common source amplifier, because we are shielding the output with the input. However, the efficiency and linearity is a poor. Now, what we have done up to all when we have discussed the all uh, the model, means all the amplifier class A, B, C, D, all the amplifier, what we have considered that its transistor, which is input impedance is a means its impedance is a constant, and its capacitor and everything is not changing as the voltage swing is changing. So, in reality it is not true, because if we consider the full voltage swing, the other the capacitor associated with the M1 transistor like CDB and the output resistance RO is also varying with the voltage swing. Now, this simplicity model assume that output matching network simply transform RL to a lower value. So, this matching network, what we have done, it just transform the RL to the lower value, that we have simplified. But in practice the situation is more complex. A non-linear complex output impedance must be matched to the linear load, because there are capacitor and the impedance is also associated. So, if we consider the large signal impedance matching, very simple case, if we consider the output resistance RO1, which is this, instead in this we are not considering the capacitor, but we are only considering the RO1, and there is a capacitor CDB1, which needs to be considered while matching to the RL. So, if we compute the power delivered by M1 to RL, which is PRL, and that consumed by the transistor output resistance PRO1, what we have a PRL output power, which is a IP square by 2 RL, and there is a VDD, which is RO1, means the voltage division rule, RO1 by RL plus RO1 whole square. This is a PRL, and PRO1, which is given by IP square by 2 RL into RO1 square by RL plus RO1 square. So, in this, in the both the case, if you write a PRL, in one of the case there is a RL which is considered, and in another case RO, means in one case RL square will be there, and in another case RO square. So, the maximum power transfer RL is chosen equal to RO1, it yields to PRL equal to PRO1. So, PRL by PRO1 equal to, so if we write PRL by PRO1, which is given by RO1 by RL square, because here there is a RL into RO1 square, and here there is a RL square into RO1. So, PRL by PRO1 is given by RO by RL. So, what the relation above show that reducing the RL minimizes the relative power consumed by the transistor. Here there is a trade off come between the maximum power transfer and the efficiency that we want to achieve. So, that we need to make sure that there is a maximum power transfer will also happen, and also we will get a maximum efficiency. So, in order to do that, we need to design a matching network such that it will be properly tuned with its output and input impedance. So, that for that we need a load pull matching, that is a load pull measurement, and this is widely used method in the power amplifier design. In order to do the in order to have the better matching for getting maximum output power and the efficiency for, for designing the power amplifier. So, here how it has been done, we have already discussed that if there is a any two port network, there is a output matching network and input matching network. This is input matching network, and then we have considered the RL, and there is a input RS, and while designing the amplifier we have discussed. Now, we also discuss that if there is a change in the uh, gamma L, means your gamma in is depend upon how we have designed the output matching network, and your gamma out is depend upon how we have designed the input matching network. So, what we need to do, we need to put a tuner. So, this is a two port network. So, this is a input means two port network. There is a tuner which will change this input impedance matching network reflection coefficient, and that is a tuner at the output which control. So, here it is shown the input resistance means RS, which is uh, RS is a constant, but here it is considered as a impedance, but we can also consider as a reflection coefficient gamma in and gamma out. So, as we are changing this control voltage, if we change the control voltage such that initially we got some power which is a P1. So, what we do, we vary the Z1 such that the power delivered to the RL remain constant and equal to P1, that is this, and thus obtaining a contour depicted. So, we make a contour, or we can also plot the power on the Smith chart. We already have seen the, so how we can do that. So, if we have a if we write a gain Gp which is equal to P out by P in. So, we can write a P out because P in already we know Gp into P in, and based on different gain circle we already have seen that Gp we can plot a different gain circles for Gp value, and that can be put on the Smith chart. So, similarly we can also plot the power P out for the different, this is a if it is the maximum power that will be shown as a dot, and for other impedance means other gains we have a different contours, and this is called a power contour, that is P1 and P2. So, the same thing has been shown here, that is a, this is a power P1 and P2, and when we have a optimum impedance at that time it will be have a dot. So, for that what we need is a load pull measurement. We need a repeated measurement at the input side and output side which increasing the power level, and eventually we want to arrive at a optimum impedance side opt to have a maximum output power. So, this kind of measurement technique is widely used when we have a transistor network available and we want to identify the matching network which is giving the maximum power for the uh, and optimum output impedance Z opt. Then we can fix the impedance matching network. Once we know this Z1 that for the tuner, that will be used to design the output matching network as well as input matching network. So, this is how load pull will work, and there are various measurement technique is provided in the literature. Now, we will discuss the basic linearization techniques, that is just I will give the brief idea. You can go in detail and understand more about it if you are interested in power amplifier design. So, one of the technique, that is a feed forward technique. Now, in feed forward technique, what we do, so there is a two diagram which is drawn here. This is a main power amplifier, and uh, whatever non-linearity which is added by this power amplifier, that will come at the point M, and this is the actual signal V in. So, what we will try to find out, that how much non-linearity will be added, we will get from by subtracting from M point, and we will put error amplifier here, which will subtract the non-linearity from the main power amplifier, and there is a subtraction needs to be done. So, here in this feed forward architecture, what it commutes the error, and with proper scaling subtract it from the output waveform. What will happen, there is a second figure which is drawn, because when you directly take this output, and if you get after the main power amplifier M, it will also observe the delay in the signal, and that delay we need to consider by using this delta 1. There is also delay, means when we use this error amplifier also, when we use the error amplifier, and that error amplifier delay also needs to be incorporated here, delta 2. Now, in order to reduce the non-linearity, in order to improve the linearity, here there are how many extra component that we are adding, that is this amplifier, and after this amplifier your V in input at Vn is equal to V in, which is this, plus Vd by voltage gain Av. So, you need this the error amplifier, 2 adder and subtractor. Now, this additional term will also consume a power, and it will reduce the efficiency. So, feed forward suffers from a several disadvantage that made its use in integrated PA design difficult. The analog delay elements introduce a loss if they are passive, or distortion if they are active. So, it will also add a loss and a distortion. Second, the loss of the output subtractor degrades the efficiency, and the linearity improvement depends on the gain and phase matching of the signals that sensed by each subtractor. So, that gain and phase matching also is important, otherwise it will not subtract the non-linearity, and we cannot get the completely linear output. So, these are the three shortcoming of this effect. Now, we will see the another method, that is called a Cartesian feedback. So, in the Cartesian feedback, what has been done, we take output, means this is a input which is coming to the power amplifier, and then with sin omega LO it is will be up converted, then power amplifier will amplify the signal. So, this we have already seen when we have discussed the transmitter architecture. As we are taking from the output some of the portion VPA, that we take to the we need to down convert that signal with sin omega LO plus theta. We do the low pass filtering, and at the we subtract input with this whatever down converted signal that we are getting, and we can see that how much error it is introducing, and we again multiply the signal and amplify the power by using power amplifier. So, if the power amplifier output is down converted and compared with the baseband signal, this an error term proportional to the nonlinearity of the transmitter chain can be created. And with a quadrature down conversion, this method, that is why it is called a Cartesian feedback. Now, Cartesian feedback avoids the output subtractor and much less sensitive to the path mismatch, but required some linearity in the PA. It can also be designed uh, that baseband, we can also make a I and Q in phase and quadrature component, and separately we can do the uh, subtraction, that is shown in the second uh, figure. Now, in this method of linearity improvement, we need to make sure that this LO signal that is a properly uh, delayed, so that the amount of down, when we are down converting the signal, it is not experiencing the delay which is added by the power amplifier. So, this is why you need to be extra careful for designing the LO, and this additional two uh, paths that we are adding in the feedback will also be uh, adding a loss and mismatch, that also needs to be considered. Another method, which is the pre-distortion, this is a widely used method because in this method simply what we are trying to do is, we know we have designed a power amplifier, and that power amplifier, how much non-linearity it is adding. So, we can plot this V out by V in curve, V out by V in. We have already known the power amplifier, we have measured the is characteristics, nonlinear characteristics, and it is defined by the function g x, if some function g x. If we try to make the inverse function of that at the input side, means the input signal whichever is coming, if we give if we pass to the g inverse x, means which is a inverted function, then what will happen, that if we combine this output, so what we are doing, we are adding the pre distortion in the incoming signal, and that pre distortion, when it is adding with the distortion, the we are getting the linearity. So, if the power amplifier nonlinear characteristics are known, so that is very important, power amplifier nonlinear characteristics are known, it is a possible to pre distort the input waveform in a such a manner that after experiencing the PA nonlinearity, it remains the ideal waveform. This pre distortion you can also bring to the digital side. Before the, means at I and Q, we make it pre distortion at the digital side, we use a digital to analog converter deck, and then there is a multiplier that can be used to up convert the signal, and it will be added and applied to the power amplifier. Now, this method has advantage if you know the power amplifier characteristics. So, there are three drawbacks of this method. The performance degrades if the power amplifier nonlinearity varies with the process, temperature, and the load impedance, while the pre distortion does not track these changes. So, if there is some change in the power amplifier due to the temperature or mismatch or the process, then it cannot, we have already pre distorted, and then the signal which is at the output will also be pre distorted. The power amplifier cannot be arbitrarily nonlinear, as a no amount of pre-distortion can correct for abrupt nonlinearity. It should not have any abrupt nonlinearity. Otherwise, there is a pre-distorted signal uh, will not, means this function g inverse into gx will not be a linear. And Variation in the antenna impedance, because we are going to connect antenna at the output, somewhat affect the power amplifier nonlinearity, but pre-distortion provide a fixed correction. What is a solution for this? In order to solve this problem, we need to add some feedback to the pre-distorted, so that this variable that we have identified in the pre-distorter should automatically change the way the power amplifier output linearity is changing. Uh, so that needs a additional feedback circuit, and the mechanism in the pre-distorter, so that this can be linearized. So, this kind of pre-distortion, digital pre-distortion are widely used, and you can go through the literature which will discuss about the pre-distortion. You can improve the nonlinearity of the power amplifier. So, and another method, that is envelope feedback. In the envelope feedback, what we do is, generally the envelope experience nonlinearity. So, what we try to do is, we detect the envelope, means there is a input voltage and then there is an envelope detector, and at the output also there is a whatever envelope with attenuation alpha, we detect the envelope by envelope detector, and there is a amplifier, error amplifier AB, which is supplied to the variable gain amplifier. So, if there is some distortion in the amplitude which is taken care by the envelope detector, if it is happening, this variable gain amplifier will change its gain accordingly, that how much is a change in the output after the power amplifier and in the difference of the input which is coming from the baseband. So, that difference will be amplified by using a variable gain amplifier. So, here in order to reduce the envelope nonlinearity in a PA, it is possible to apply a negative feedback only to the envelope of the signal instead of considering the phase. So, only we will play with the amplitude. And how does the distortion of envelope detector affect the performance of above system? If the two detectors remain identical, their distortion does not affect the performance, because the feedback loop will yield a VA is equal to VB, and hence if VD which is equal to V in, this property proves greatly helpful here, as a typical envelope detector suffers from a nonlinearity. So, we need to ensure that envelope detector is identical. If it is identical, it will have a, and we need to attenuate alpha, then this V in should be equal to V t. There are different kind of method by which we can design an envelope detector. The simple method is, we give the mixer input, will be input and LO signal will be shorted. It will use a square, so squaring of the signal. So, what we are doing, this is a V in t, which is V envelope cos omega naught plus phi t. If V out t, which is a square, because two signal are multiplied, beta with beta V envelope square t cos square omega naught t plus phi t. So, what you will get a envelope in the DC plus cos 2 omega t plus 2 phi t. So, you need one low pass filter which will passing out the second and other harmonics, then you will get a envelope at the output. You can also use a simple source follower in order to get only the envelope. So, this will track the envelope, not the carrier. You can also use a limiter circuit. This is a limiter circuit by using a differential amplifier, and then this is a simple multiplier, Gilbert cell multiplier, that we have discussed, and that will V in, means when it is limiter is applied, and VA and VB which is a multiply, you will get the envelope output. That also needs to be low pass filter. So, limiter and mixer can also be combined and used as a envelope detector. So, in practice the limiter may require 2 or more cascaded differential pairs. There is another method by which we can improve the non-linearity in the power amplifier. What we can do is a polar modulation, where we change the phase and amplitude envelope, and then we try to change the amplitude of the power amplifier with the envelope. So, any band pass signal can be represented in terms of V envelope cos omega t plus phi t, and we decompose the input into an envelope signal and a phase signal, amplify each separately and combine the results at the end. So, this approach is called a polar modulation because it possesses the signal in the form of a magnitude, possesses a signal in the form of magnitude, envelope and component and a phase component. So, this is how this is input where envelope detector, it is applied to the switching PA, and this is a phase which will be amplified. So, this is how we can design the polar modulator. And the final is a method which is a outphasing. Now, in outphasing what we can do is this is a basic idea. We will discuss about more about outphasing, and one of the widely used power amplifier, that is a Doherty power amplifier, in the next class. Thank you.